Okay. Now, you will be able to see these expressions how it is done. So, f minus f I comma I cross 1. So, this minus and this minus f I is acting to the point of contact, and this is the point about which I am calculating. So, A I cross this vector. So, A I cross minus of this, then this is m g. So, this is my d I, and so m g is acting like this. Okay. So, at that point of contact, so that is why I have written d I cross m I g. Okay. So, now I go back to my presentation. Okay. So, this there is some problem. One moment. I think there is some mistake in the equation. Okay, yes, this will be this. Okay, there is a mistake in the expression here. So, this will be minus. Okay. So, now what I have done it is, I have written down the equation which I have just written for you on the paper. Now, I have just rearranged it. The first one, so this first one I have rewritten keeping f I minus I comma I in the left hand side and taking all others on the right hand side, and similarly this one keeping that one on the left hand side, taken rest on the other side. So, that gives me the force and the moment acting on ith body. So, starting from the first body, starting from the last body, because if I am carrying some weight here, I know what this is the external force acting here. From the force and moment balance of this one, I can calculate that what is the force and moment are acting on this body, and then knowing the force and moment on this body, which is applying to this body as well, my upper arm, I can calculate what is the force and moment at this junction, and then I am completely knowledgeable about total forces and moment acting this side of the link, this side of the link, and this side of the link. Now, the question is how much is the torque. So, if I know how much is the moment acting on this joint, that means my elbow joint, if I know that how much is the force and moments acting on this joint, then the moment about the z axis, okay, which is the allowed motion. So, if I know that how much torque has to be applied about this axis, this moment has to be provided by the motor. If it is not provided by the motor, it will start falling like this thing, right. So, but other forces will, since motions along the x, y and z are not allowed, because this body will resist them. So, whatever moment I calculate at this point, elbow point, the z axis, okay, the z axis will be the torque required by the motor. Please think on that thing, and if you have difficulties in understanding, we will discuss it later. So, what I have written down at the bottom here then, joint torque tau I is nothing but E I transpose n I minus 1 comma I, which means E I is the unit vector along the axis of the ith joint. Its dot product with n I minus 1 comma I, which means if you calculate them in the ith frame, I will show you in the paper. So, what I am writing here is as follows: tau I is equal to E I transpose n I minus 1 I. Okay. So, this means actually is something like this. If this is your E I, that means ith joint, the n I minus 1 I is there. Now, this has a 3 component. So, let us say this is x component, this is y component and this is z component. Now, along these directions the body cannot move with respect to the previous body, right. Along x it cannot move, along y it cannot move, only about z it can move. So, if you let it free it will start moving it, but since it is in static equilibrium I need to provide a torque which is equivalent to Niz. So, now if I calculate E I in ith frame and n I minus 1 in ith frame. So, we know this will be 0 0 1 and this will be n I minus 1 I x component, n I minus 1 I y component and n I minus 1 I z component. So, if you perform these operations you get n I minus 1 I z. So, in a way if I have calculated this thing from the force and moment balance, if I want to know what is the torque to be provided at the ith joint to resist the end effector motion, then the result is simply I minus 1 comma I, the z component, right. If it is a prismatic joint, no, it will be simply for this is for revolute, this is for revolute, for revolute. If it is for prismatic, in this case it will be called as the force F I minus 1 comma I z. Okay. So, as in many of the examples I am avoiding the prismatic jointed one. So, for the time being you understand the top portions. If you understood the top portion, the bottom portions will not be difficult for you to derive. So, go to the presentation again. So, this is basically our recursive equations. That means, write the force balance, then write the moment balance, and then from those force and moment balance we can calculate each joint what are the force and moment. For revolute joint we know it will be the third component of the n I minus 1 to I, and for the prismatic joint it will be the force component, the third force component of this thing. So, we will take an example now. Okay. I think with this example it will be clear for you to understand how this is going on. Okay. So, let us take our very favorite revolute example. Okay. So, here you have revolute. So, revolute joint here, and so you have a revolute joint here, you have a revolute joint here, okay. And then we said there is a force applied on it. This is the force applied on it. It will has a x component, it will have some y component, it will have some y component here. Given f x and f y, but then this f x and f y will be measured in which coordinate frame, right. Assuming you have a transducer here, a torque sensor or a force sensor, it will be easy to measure in this coordinate frame. If you have a force sensor here, then you know what is the force applied in this direction and applied in this direction, which is nothing but the measurement of the force in the third coordinate frame here. Okay. So, F should be given in the third coordinate frame, that means their representation in x3 and y3. Having given that force, I want to know what is the torque to be applied here and what is the torque to be applied there in order to have the static equilibrium. Now, this could be a scenario as I have shown, carrying a weight in a static positions, or maybe try to push a wall against some say glass screen. Okay. So, now we go how to solve the problem. For your information, for simplicity, I am assuming that it is moving in a horizontal plane, that means no gravity. So, we do not have any gravity here. So, no gravity is assumed, that means g, the acceleration due to gravity is equal to 0. Now, F23 is Fx Fy. What is F23? So, if environment, so if I am carrying a load here, okay, this is applying a force on this end effector, and end effector is having a equal opposite force. Sorry, let me correct it. Okay. Okay, I redraw it. So, let us say the end effector is pushing against a wall. So, wall is applying this much force, and so the reverse force according to Newton's third law is that one F. That F components we are assuming as Fx and Fy. So, that means body 2, this is my body 2, this is my body 2, that is applying to a maybe a third environment which is sitting there. So, body 2 applied on body 3. So, this F is equivalent to this F is equivalent to this is equivalent to. So, this is equivalent to that the body 2 applied on body 3 measured in third frame, because as I told you that is a force transducer, the component is Fx and Fy. Now, so these two are my known quantities and I have to calculate the torques. So, now I apply my this formula which you have seen it here. So, F I minus 1 comma I. So, now in 1 2 3. So, this is my F 2 3. So, this will be my F 1 2. So, G is 0. So, this gets cancels out. So, F 2 3 is equal to F 1 2. So, that is the same thing I have done it, that F 2 3 is equal to F 1 2, but because 2 3 is known in frame 3, I wanted to know its values in frame 2. So, I have multiplied by Q 2. This we have discussed in detail what is the meaning of orientation matrix. Meaning of orientation matrix is, if you know the information in one coordinate frame, if you want to know the same information in another coordinate frame, you multiply with the orientation matrix. In this case, F 2 3 was provided in frame 3, which is here, and I want to know in frame 2. So, I multiply with Q 2. Let me show you with my hand calculation here also. So, this is my F, which is Fx, Fy and 0. Okay. Now, this F is actually force F 2 3, that means body 2 applied onto another body third, and this is measured in third coordinate frame, and so this will be f x f y 0. Now, as per our formula, f I minus 1 I is equal to f I comma I plus 1 g is 0. So, this is actually will give me f 1 2 f 1 2 is equal to f 2 3. Okay. Now, f 2 3 is here, f 2 3 in 3 is f x f y 0. I just took it from there, but I want to know f 2 3 in 2. As per our orientation matrix definition, it should be f 2 3 in 3. Now, what is q 2? Q 2 is the rotation between this coordinate frame, right. This is q 2 and this will be q 1. So, q 2, we know what is q 2, I will write q 2, we have done it sufficient times earlier. Q 2 will be cos theta 2 sin theta 2 0 minus sin theta 2 cos theta 2 0 0 0 1. Okay. So, now f 2 3 in 2 should be cos theta 2 sin theta 2 0 minus sin theta 2 cos theta 2 0 0 0 1 and f x f y 0. So, this will give me f x cos theta 2 minus f y sin theta 2, this will be f x sin theta 2 plus f y cos theta 2 and 0. And now, as per the force balance, f 1 2 is equal to f 2 3, which means f 1 2 in 2 is equal to f 2 3 in 2 and which is equal to. Okay. And this is the expressions I have written on the screen. If you note it, f x cos theta 2 minus f y sin theta 2, f x sin theta 2 plus f y cos theta 2. You see now my screen. So, f x cos theta 2 minus f y sin theta 2 and f x sin theta 2 f y cos theta 2. Okay. So, knowing the external force applied on the end effector, in other words, knowing the end effector force on the environment, I calculated what is the force applied at this joint. That means, what is the force applied by first body to the second body. Now, let us go for the moment equation. So, for the moment equation, we look at here, again g is 0. So, we do not care about that part. So, c is 0. So, we do not care about that part, only we cared about this part, we care about this part and this part. Now, f 2 3, if I is equal to 2 and I plus 1 3, we have not considered any external moment, which means there is in this diagram I have considered only external force. So, there is no external moment, that means nobody is twisting it, nobody is trying to rotate it, right. So, n 2 3 is 0 for me, n 2 3 is 0. So, if n 2 3 is 0, which means this component, so this component is 0 for me. So, only thing which is remain here is A 2 cross f 2 3 and here N12. So, N12 will be equal to A2 cross F23. Okay. So, that is the calculation I need to do. So, that is the calculation I am doing it here. So, A2 cross F23. I have calculated it in frame 2. A2 in frame 2 I will see what it is, so that I can calculate N12 in frame 2, okay, because all the vector quantity should be in the same frame in order to calculate. So, A2 in 2 is nothing but the fourth column of your T matrix. So, the T matrix, homogeneous transformation matrix we have. Okay. So, this is just the fourth column. If you look at it, so if you divide it into this, so this column will be your A2, which we know from our kinematic study. So, I took this value and then F12 into, if you do the cross product, you will get F2 Fy. Let us do these things together, so that it will be very clear. So, come to the screen again. So, A2 cross F12. So, everything in 2. So, I do it A2 cos theta 2, A2 sin theta 2 0 cross Fx, we had Fx cos theta 2 minus Fy sin theta 2, okay. Then Fx sin theta 2 plus Fy cos theta 2 0. Actually, for the cross product formulation, I first do this minus this. Okay. So, the first component will be 0 0. Then I will be doing this minus this. Okay. So, that will be again 0, and the last one will be this minus this, which is very similar to what we do ijk, no, suppose two vectors, first component, second component, third component, maybe x, x2, x3, y1, y2, y3. So, keeping it row wise, I am putting it in the column wise, and the formula I am using. So, this one will be your A2 Fx cos theta 2 sin theta 2 cos theta 2 sin theta 2 plus A2 Fy cos square 2 minus A2 Fx cos theta 2 sin theta 2, and then minus plus A2 Fy sin 2 square. I will bring it to the left. Okay. So, now you see this and this cancels out. So, what we left with 0 0 A2 Fy cos square theta 2 A2 Fy sin square theta 2. So, it will be A2 Fy. So, N12 in 2 is our 0 0 A2 Fy. Go to the LCD. So, this is the value you get A2 Fy, and how to get it I have shown you, right. So, that gives, look at my hand now. So, I started from here, that Fx Fy is applied to the environment like this, and that is to basically the resist, this one. From there I calculated what is the force F12 and what is the moment F12 N12. Now, this is a two link problem. So, now I come here, what is F01 and what is N01 in a similar manner. That is my next slide. So, again I apply the force balance equation, which is this one here, that F12 here should be equal to F01 because no gravity. So, I go there. So, I calculate what will be. So, F12 is equal to F01, but because F12 was known in frame 2, I would like to know in frame 1. So, I multiply with Q1. Okay. So, after doing these things, we can find out that this will be the expression for the first component of F01, the second component of the F01. Now, if we look at the moment component now, so this will be N01 should be equal to N12. Now, I have some N12 value calculated in the previous step, then this will be A1 cross F12, again Z is 0. So, we do not bother about it. So, now I have calculated N01, I am interested in frame 1. So, N12 if I knew in frame 2, I would convert into frame 1 by multiplying with Q1. A11 I know from the homogeneous transformation matrix, F12 in 1 I would know from this stage because F12 in 2 I have converted by multiplying with Q1. So, the whole thing will now look like the expression shown here, and the final equation is calculated there. You can check if anything wrong. If there is something wrong, you can report to me. So, now what I did, so I have calculated at all joints knowing what is the force applied on the end effector. So, now the torque 1, as I told you earlier, is nothing but the Z component of N01. So, the torque 1 will be, so this should be your the torque 1, okay. And what will be torque 2? Torque 2 will be the third component of N12, which means this will be your, so this will be your torque 2, A2 Fy, okay. So, that is the expression which is calculated here. The torque 2 is A2 Fy and torque 1 is equal to whatever is shown. If you would like to verify quickly whether my equation gave the correct result or not, I can go back to my one of the figures, okay, and see whether this is right or wrong. Okay. Let us go back to the two link figure. Let me go back. Okay, here is my figure. So, now if you look at it, F has a component along x and y. Okay, let me try to draw. So, it has a component Fy and then Fx. Now, imagine that this is the force is here, which is trying to rotate this link in these directions. Okay. So, if I have to resist, what is the torque being applied here? So, that torque is, this is my Fy, this is my Fy, and this is my perpendicular distance, right. So, A2 Fy. So, A2 and Fy is being applied to resist the force which is going in this direction. So, environmental force or the external force is acting in these directions, and this end effector is opposing this due to the application of torque here and there, but I am presently interested to the what is the torque should be applied here. Now, to resist this force, the component is Fy and this distance is A2. So, A2 Fy should be applied by the second joint. From the geometry I find it, and if you look at the expressions, if you look at the expression, you see this is the A2 Fy. So, now from the geometry it makes sense that okay, the torque 2 to be applied is A2 Fy. Similarly, you can find out from the geometry also that this will be the torque to be applied by the first joint. Okay. So, that way my static calculation is finished. If a robot has to resist or carry a load, then torque 1 and torque 2 for the 2 degree of freedom robot manipulator I have calculated. Many times statics calculations are sufficient for a robot design when robot is moving very slow. When the robot is moving very slow, that means the dynamics can be ignored. Okay. If there is no acceleration, means it goes very slow. Many times we carry only static analysis for the design of link material, link lengths and link lengths or the motor selections. I stop for a while here before I go to the next exercise. If there is some questions or difficulties, please ask. No difficulties? Be little louder. Examples? Sorry? This is good? Sorry, actually it is not. I can hear you only, but not the words. Okay, I can proceed. Good. Okay, so next look at the next example, which now has a prismatic joint. Okay. So, it is a revolute and prismatic. Okay. So, there is a small corrections if you are using the first 2008 version of my book. In 2008 version of my book, there is a small mistake. X3 it was an X3 here, X3 was also here, which is wrong. X3 would be here, as I have corrected here, and the corrected figure is uploaded. Okay. So, first we put the DH frames as we have done it in earlier situations in order to do the kinematics. After we have put the DH frames, we have indicated the DH parameters, and now for the static purposes I assume a force F has to be applied by the end effector to resist certain force, maybe the weight. Okay. So, this is the environmental force I have indicated with E N V. So, this may be environmental force, and that has to be registered by a force to be applied here, and that force has to be created by a torque here and then a force at the prismatic joint. My task is to calculate what is the torque here and what is the force by the prismatic joint for the revolute prismatic arm. Procedure is exactly same as before. Let us look at those steps. Okay. Here you have to be careful about the coordinate frames, because this is my Z3, this is my X3. So, if a force is applied by the end effector on the environment, so this will be Fz component, this should be Fx component, and there is no Fy component because it is a planar. So, if you see, so this is Fx component. So, we have Fx component and Fz component, no Fy component here, right. Using the similar formula, F23 is equal to F12, but if I am interested to calculate it in 2, I have to multiply it by Q2 to get my F23, and Q2, if you notice, Q2 is what? Q2 is the orientation between frame second and frame third. Now, X2 is parallel to X3. Now, X2 is parallel to X3 and Z3 is parallel to Z3. Obviously, then two coordinate frames are parallel. So, parallel means Q2 is an identity matrix. So, for that purpose F12 into and F23, if you convert, it remains the same result as you see there. So, Fx 0 and Fz. Now, A2 into, if you look at your transformation matrix for the RP, the fourth column is 0 0 B2, that is your A2 in 2. So, for the calculation of N12 in 2, we do the same calculations as we did earlier, but with the new values of A2 2 and F2 2, and this will give you this expression 0 B2 Fx and 0. Next, I go in the similar manner that F12 is equal to F01, and then I want to convert from frame 2 to frame 1 by multiplying with the Q1, and then this is the relation I get it. Okay. Let me do this thing for you. So, Q1, since this is an RP, so Q2 already I have told you this will be 1 0 0 1 0 0 0 1, Q1 is equal to cos theta 1 sin theta 1 0 minus sin theta 1, oops, this is wrong. Q1, what we have calculated earlier was cos theta 1 sin theta 1 0, we have 0 0 1, then we had sin theta 1 minus cos theta 1 0. This is as per DH parameters of RP arm. Okay. Now, F12 F01 is equal to F12. Now, F12 into was known as F12 was known as Fx0 Fy. Okay. Now, I want to calculate in F12 1, which is Q1 F12 in 2, which means these two have to be multiplied, right. So, the results Fx cos theta 1, Fx cos theta 1, I am writing C1, then plus, let me rewrite, this is too small here, F12 in 1 is equal to Q1 F12 in 2 is equal to cos 1 sin 1 0 0 0 1 sin 1 minus cos 1 0. We have Fx 0 Fy. This will be calculated as Fx C1 plus Fy sin 1 Fx sin 1 minus Fy C1, and this will be 0. Okay. So, F12 in 1 is calculated as that, N01 in 1 can be calculated as N12 in 1 plus A1 cross F12 in 1. Okay. So, N12 in the previous step it was known in 2. So, I have to multiply N12 in 2 plus A1 in 1 cross F12 in 1. So, F12 1 is known here. So, this will come there. A1 1 I can calculate the fourth column of T1 and this previous step, and I know Q1 is this one. Okay. So, now if you do these operations, the final operation is shown on my slide, which you can see. So, the final operation is very simply can be written as 0 0 and B2Fx. So, now the question is, what are the joint torques or joint force here? As we have done in the previous example, the joint force for the prismatic joint is nothing but the third component of F12. F12 means first joint applied to second joint. Okay. So, F12 we have calculated here. So, F12 we have calculated here, that this is my F12, that means link 1 applying force on link 2 due to the prismatic joint. So, the force to be applied by the prismatic joint is equal to Fz, and I have written it here Fz. So, indicated with tau 2, that means tau 2, even though it is written as a tau, it means the force to be applied by the second joint. If the second joint is a prismatic joint, tau means the force applied to be second joint. Now, then for the first joint, tau 1 should be the third component of N01. So, third component of N01 is B2Fx, B2Fx. Let us go back to the diagram and see whether it makes sense or not. So, we go back to the diagram. So, now look at it. If I have a force applied, by the environment here, the resistance is done by this F, and this F has a component F z, and if I want to create F z, obviously I need a F z component to be delivered by my motor, right. Then if this is my F x, obviously F x into B 2 will be the motor torque to be delivered by my first joint. And now very interestingly, you see these are the two results, and you see these are the two results. F z is the prismatic joint force and B 2 F x is the first joint torque. Okay. So, with these two examples, I think the steps will be clear, and now I have an assignment for you. This is assignment number 3. I have not evaluated for first two, even though I have given some marks, but I have told you that they will not be counted toward the final grades. But here I have assignment 3, find the joint torques for the revolute planar arm if no external torque is applied, that is N 3 4 is 0 0 0. This problem is solved in the exercise with a different input. Okay. In the book you have external force as well as external torque or external moment, but in the assignment I am asking you not to consider any external moment, consider only external force and do the job. Duration is 1 week, that is due on 3rd August 2009 Monday. Please keep it ready. I may ask by some means to show or submit, okay. And this time I may consider the marks in the final grade. So, I will wait about 30 seconds here. If there is any questions till you note down the assignment 3. This is actually your example 7.3 with the different input data I have provided here, that means no external moment. So, if there is no further questions, so I stop saying the summaries. Link forces and moments are written for you in static equilibrium, recursive relations are shown, RR and RP examples are done in details, and one assignment is given, and I would like to thank you for today's class.